Hey everyone! So, what if we could build our planet's entire operating system completely from scratch? Well, that's exactly what we're going to try to do today. We're going to reconstruct Earth's geodynamics using nothing but the most basic, fundamental laws of physics. Our whole journey, it really just starts with one simple question. The most fundamental question you could possibly ask about a planet like ours. And trust me, everything we're about to get into, volcanoes, earthquakes, you name it all starts right here, with this one simple thought experiment. But to answer that question properly, we have to do something, well, kind of radical. I need you to forget everything you learned in school about tectonic plates. Seriously, just for the next few minutes, wipe the slate clean. We are not starting with plates. We're gonna see if we can end up there. Okay, so if we're not starting with plates, where in the world do we begin? We start with the most basic, undeniable laws of the universe. This isn't geology. Not yet. This is pure physics. All right, so here's principle number one. The Earth began as this molten ball of rock, right? Incredibly hot. And its surroundings, the vacuum of space, are incredibly cold. And as we all know from basic thermodynamics, heat always flows from hot to cold. That massive temperature difference creates this constant, relentless pressure for all that energy to escape from the planet's core and radiate out into space. And let's be super clear here. We haven't mentioned a single rock type, not one geological feature. This is all just about heat. This is the fundamental engine that drives, well, everything. The planet has to cool down. The only question is, how? So this brings us to a concept that's, honestly, it's a little hard to wrap your head around. I mean, rock seems solid, right? It's a great insulator. But it's not perfectly rigid, not at all. Over these immense geologic timescales, we're talking millions of years, and under the incredible heat and pressure deep inside the Earth, solid rock actually behaves like a thick, gooey fluid. The best analogy? Think of it like cold honey. It moves so slowly, but it does move. And that's pretty much the state of the Earth's mantle. It's not a liquid ocean of magma. That's a common mistake. It's a solid. But it's a solid that is constantly churning and flowing, driven by that relentless need to lose heat. And that internal movement, that's the key to everything. Now, this whole process actually has a name. It's called mantle convection. And you've seen this before, right? It's just like a pot of boiling water on the stove. The hotter, less dense material rises up, and the cooler, denser material sinks back down. This creates these massive, messy, churning currents inside the mantle. And this circulation, it's the direct physical result of those first two principles we just talked about. Okay, so we've got it. We have this churning, flowing engine deep inside the planet. So now let's follow the consequences up to the surface. Let's see how this incredible internal motion forces a really dramatic response on the outside. See, the planet's surface, what geologists call the lithosphere, it's a completely different beast. It's been exposed to the freezing cold of space for billions of years, so it has cooled way down, becoming totally rigid and brittle. So you've got this fundamental conflict, right? A soft, flowing interior dragging along a cold, hard, brittle shell. And this leads us to the absolute crucial question. What happens when you have this immense, slow-moving engine of the mantle trying to drag a cold, brittle lid around? Well, something's got to give. And here is the inevitable conclusion. The stress just becomes too much. That rigid outer shell has absolutely no choice but to fracture. And in that one moment of breaking and sliding and sinking, plate tectonics is born, not as some feature that was always there, but as an absolute physical necessity. So the key takeaway here really is this. Plates are not the starting point of the story. They are the result. They're the most efficient solution the planet could come up with to solve its fundamental problem, how to lose all that heat. You see, breaking the surface into these giant pieces allows cold, dense rock to sink back down and hot mantle material to rise up. It's kind of like opening up vents on a giant planetary radiator. All right, so now our planet has found its solution, a broken, moving shell. But what are the rules that govern this new reality? What does life on a broken sphere actually look like? Now, you might think the forces are all nice and balanced, but the system is surprisingly one-sided. The single most powerful force driving the motion of these plates is something called slab pull.
See, when a piece of that cold, brittle crust starts to sink back into the mantle, it becomes way denser than the hot rock around it. So gravity just takes over and yanks that sinking slab down with incredible force, dragging the rest of the plate along for the ride. It's the sinking that really drives the whole show.
And there's this really beautiful geometric consequence to all this motion. You can't move in a perfectly straight line on the surface of a sphere, right? It's impossible. Any movement from one point to another is actually an arc. It's a little segment of a giant circle. And what that means is that every single plate's motion can be described as a simple rotation around a specific point, which we call an Euler pole. And this isn't some complicated math trick. It's just the unavoidable geometry of living on a ball. Okay, let's put it all together. We've taken simple physics, heat, pressure, geometry, and just piece by piece, we've built the entire dynamic system of our planet from the ground up. This really just sums it all up, doesn't it? Every single mountain range, every earthquake, every volcano, it's all just a surface-level expression of this one deep, continuous process, a planet trying to cool down. That's it. If you're going to remember just one thing from all of this, let it be this next analogy. It's so simple, but it perfectly captures this entire complex process. I want you to imagine a freshly baked apple, steaming hot right out of the oven. As it sits there, its outer skin starts to cool down really fast, right? It gets stiff, it gets wrinkled. But the inside, the pulpy part, is still super hot and it's shifting around. And eventually, that brittle skin just can't handle the strain from all the movement inside and it cracks. Those little pieces of skin start to slide around, they bump into each other, maybe one even gets pushed underneath another. That apple, that's our Earth. And that right there, that's the ultimate shift in perspective. Plate tectonics isn't some feature that was designed into the planet from the start. It's what we call an emergent property. It's the inevitable outcome of a few simple physical laws just playing out over billions and billions of years. And that leaves us with one final thought. This whole way of thinking, breaking down a really complex system to its most basic first principles and then just seeing what emerges. It's an incredibly powerful tool. So it makes you wonder, what else in our world, from economies to ecosystems, isn't really a fundamental thing at all, but is simply the result of a few simple rules running for a very, very long time?